Hey friends, welcome to my channel. So this video I will be talking about very important thing because many people several times ask me that how to start reading organic chemistry from the beginning or how to read the Claydon book. But how to read Claydon book, that is a very fuzzy question. Everyone has a different technique for reading a book, so you should find it for your own. But then I thought that what I can do best is that I can start from the very beginning of the organic chemistry, that how I read, and that will help you a lot. So from this video I will be talking about the at the very beginning of the organic chemistry, like for the from the basic principle of the organic chemistry, the bonding, the structure of molecules, because before knowing about the reaction you should know about the structure of the molecule, the concept of the molecular orbital theory and that thing, and these all things I will be covering in this video series. So I will be uploading one or two videos on this particular series in a week, so that may be on Sunday and Saturday, but I am starting from today. So you should watch this video carefully, and I will cover all the important things from starting from the very beginning. So in today's video I will be talking about the structure of the molecules, that how a molecule is formed by the interaction of orbitals, how molecular orbitals looks like, what are their importance in a reaction, how reaction happens, and what are the concept of nucleophile and electrophile. So first of all, if you know about the basic principles of the chemistry or basic principles of the structure of the atoms, you know that every atoms have several orbitals around it, and they are s orbital, p orbital, d orbitals, like this. Now and these orbitals have different shapes. For example, your s orbital has a spherical shape, your p orbital has a dumbbell shape, and your d orbital has two lobes here, like that. So in our organic chemistry we will be basically focused on the carbon molecules, the molecules formed by carbon and some of the other atoms. So basically we will be talking about s and p orbitals. Okay, so how a molecule is formed. So I will be not discussing any mathematical things in these videos or in this discussion. I will be just telling all the things in terms of organic chemistry point of view. Okay, so all will be qualitative discussion, no quantitative or mathematical discussion will be there. So and that will be more easy to understand in terms of organic point of view. Okay, so let us first discuss that how a molecule is formed. Let's say when two hydrogen atoms comes closer, we know that if two hydrogen atom comes closer, H2 molecule will form, and this interaction is basically, let's say this is your one hydrogen atom and this is your another hydrogen atom. So if you bring them closer, so they will interact and a H2 molecule will be generated. Now you know that if two orbitals interact, two new molecular orbitals will form. So interaction of two atomic orbitals will generate two molecular orbitals. So one is bonding orbital, another one is anti-bonding orbital. Now how this happens? So you know s orbital we can represent like this. This is the wave function of the s orbital. So now when two s orbitals comes closer, these wave functions can either interact constructively or they can interact destructively. So if they interact constructively, you can see the wave function between these two atoms grow up, or the wave function, coefficient of the wave function increases. That means it is a constructive interference and we say a bond is formed. Whereas if they interact destructively, let's say this like this, so then you can see a node is formed here, so no bond will form, and this is called destructive interaction. So we can pictorially represent like this. So let's say this is one s orbital, this is another one s orbital. So they can interact constructively to form a bonding molecular orbital, which we call sigma, and another way they can interact like this, and this is called anti-bonding molecular orbital. So this is destructive interference like this, and this is the constructive interference. Now if we show it in terms of picture of the orbitals, so let's say this is your one s orbital and this is another one s orbital. So if these two are when they are interacting, if the sign of these two orbitals is same, let's say in this case both have white color, so then the interaction is constructive interference. Whereas if their phases are different, so let's say it is white whereas it is black, People may represent it like plus plus and plus minus, but I prefer black and white formalism. And let's say they interact like one is white and another one is black. So now you can see no bond is formed between them because symmetry doesn't matter. So they cannot overlap, and that is called destructive interference, and it will lead to the anti-bonding situation. So every time when two orbitals interact, there is a situation of bonding and another one is anti-bonding. Now anti-bonding situation means it is a stabilizing situation. That is, you can see another way we can say that if two orbital interacts, energy of one orbital will lower and energy of other orbital will higher. Now let's say both of these orbital brings one electron with them, and we know we can put one electron in the same orbital by the spin pairing. Now in the resulting molecule you can see two new orbitals are formed. One is bonding and another one is anti-bonding. So it will be a wise choice to put these two electrons in the bonding orbitals, because you can see this has the lowest energy orbital among all the orbitals here. So this is how a bond is formed between two molecules. That is, whenever the electrons are occupied in the bonding orbital, we say that bond is formed. Now let us talk about sigma bond and pi bond. So let's say a p orbital, two p orbitals interact head-on overlap, and whenever head-on overlap will occur, so this is called sigma orbital. And if the overlap is lateral or sideways overlap like this, so you can see this way also the overlap can occur, and this is called a pi bond. Now obviously you can see the sigma bond will be stronger than pi bond, because this lateral due to this lateral or sideways overlap, there is always a node between these two molecules or these two orbitals, but you can see in this case there is no such node. So obviously sigma bond will be stronger than pi bond. Now let us come back to the situation of H2 molecule. So this is a representation of H and H which form H2 molecule. Now one thing you should notice is that due to the conservation of energy law, we can say that whenever two orbitals will interact, they will always form two molecular orbitals, not more than that or not less than that. And another important thing is that the energy which is lowered by the formation of the bonding orbital will be always same with the energy which is risen by the formation of the anti-bonding orbital. That is, this delta E and this delta E will be same. But there is a condition that when you don't fill this orbital with the electron, then only you can say that this delta E and this delta E will same. But if you fill this bonding orbital with two electrons, then the situation is something different. That is, at the time you fill this bonding orbital, its energy will be slightly upward. That is, now the delta E will turn into delta E dashed, and in this case this delta E dashed will be lower than delta E. That means if this orbital is filled with electron, then the energy which is lowered by the formation of the bonding orbital is lower than the energy which lower than the energy risen by the anti-bonding orbital. Now why this is so? So this is because whenever you are putting two electrons in the same orbital, you have to consider one extra term in your overall energy of the orbital, and that is the repulsive energy which is generated by placing two electrons in the same orbital. Because if you put two electrons in the same orbital with opposite spin also, there will be a Coulombic repulsion between these two electrons, and you cannot eliminate that Coulombic repulsion by any way, and that will contribute to the overall energy of the orbital. So the energy will be raised. But you can see, as this is vacant, then there is no such situation, and so this orbital will be energy of this orbital will be same as it was previously. So this is why you should always remember that if you fill the bonding orbital with some electron, its energy will be slightly higher than what would be the case without filling. Now this is the situation of H2 molecule. So here we can say that why helium-2 doesn't exist, He2 doesn't exist, because helium-2 already has two electrons with two helium atoms, and now by the formation of the molecular orbital, you have to place the two electron also in the anti-bonding orbital. You can see overall the energy lowered by the formation of the bonding orbital is compensated or exactly compensated by energy rising of the rising due to the placement of the electrons in the anti-bonding orbital. So overall, the overall stabilization will cancel out and no net gain is there. So that's why they will not form any bond. So this is very basic things. Now let us come to our organic chemistry, and in our organic chemistry we will be basically focused on the bonds like CC bonds or CH bonds like this. So in this regard, I will first talk about the formation of the formation or the drawing of the molecular orbitals for diatomic molecule. For example, C2, B2 and N2, and also O2 and F2. And then I will also talk about the formation of the molecular orbitals for CO and NO, because these are basically the questions from this topic comes in the inorganic chemistry, but also you should know that before knowing about the reaction mechanisms. Okay, so let us first talk about the molecular orbital diagram for these diatomic molecules. Let's say diatomic boron, diatomic carbon and diatomic nitrogen. Why they are different from these two, oxygen, fluorine, it will be clear in a moment. So in this particular molecules you can see there are 1s orbital, 2s orbital and 2p orbitals, but 1s orbital is too low in energy and that's why it will not participate in bonding. So we have to consider only 2s orbital and 2p orbital. So whenever a diatomic molecule is forming, let's say for example boron. Okay, so two boron atoms are interacting, so we can represent boron's 2s orbitals here like this 2s orbital and the 2p orbitals here. Okay, so these are the 2p orbital. One will be like this, another will be like this and another will be like this. Okay, so now we have to fix some axis. So let's say this is the z axis, this is the y axis and this is the x axis. Okay, and if we are considering that molecules are interacting in the z axis or along the z axis. Okay, so these z orbitals will form the sigma bond and the other two orbitals will form the pi bonds. Now if we consider the symmetry of the 2s orbitals, this is 2s orbital, these are 2pz, 2px and 2py. So if we consider the symmetry of the orbitals when they interact along the z axis, the symmetry of the 2s orbital and the pz orbital, they will permit to overlap among themselves. That is, these two pz orbitals and these two 2s orbitals, they can overlap to form 4 molecular orbitals. 4 atomic orbitals can interact to form 4 molecular orbitals, and we will represent them like this. So this is the first orbital, this is the second orbital, this is the third orbital and this is the fourth orbital. Now all these 4 orbitals are contributed with these two 2s orbitals and these two 2pz orbitals. So we should connect them with all these orbitals because they all are contributing, although the contribution will not be same amount, but still they are contributing. So that's why we should connect with these dotted lines here. Okay, so this represents that by combining these all 4 orbitals we are generating these 4 molecular orbitals, and then these two p orbitals, namely px and py, they are left and they will form the pi bond. So we represent the pi bonds here. Okay, so these are the pi bonds. Okay, now we will name these orbitals in the along the order. So this is 1 sigma, this is 2 sigma, this is 3 sigma and this is 4 sigma, and this is 1 pi, this is 2 pi. Okay, now one thing you should notice that this 4 sigma is actually sigma star orbital, that is anti-bonding orbital, and 2 pi is actually pi star orbital, but we are not consider doing the nomenclature like pi star or sigma star. We are just showing in the order of higher energy by putting 1, 2, 3, 4 like that. So 4 means it has higher energy, 1 means it has lower energy. So this is another way of representation, and you can get this representation in the V book. Okay, So it is a more simple way of representation. Now for your boron molecule, you know that for boron molecule 2s orbital has 2 electrons and 2p orbital has 1 electron. So overall 3 electrons are there. So for 3 electrons for one boron and another boron, you have another 3 electrons. But when you are filling the molecular orbitals, you don't have to consider about atomic orbitals. You just have to focus on the molecular orbitals, and the 6 electrons, all 6 electrons you have to place according to this energy order. So this is actually the energy axis. So now obviously first 2 electrons will be placed in the 1 sigma, then another 2 electrons will be placed in the 2 sigma. Now you have another 2 electrons left because you have total 6 electrons. And here you can see this 1 pi orbital, although 2 pi orbitals are there, but they are degenerate. So you have to place the orbitals in 2 separate orbitals, that is one in this pi orbital and one is this pi orbital. You cannot put them in the same orbital because Hund's rule says that whenever you have 2 or more degenerate orbital, you have to always place the orbital as singly occupied, or you cannot pair them. Okay, so this will be the electronic configuration of the B2 molecule. Now from this electronic configuration you can see that B2 molecule will be paramagnetic because it has 2 unpaired electrons. Okay, now when you change boron by carbon, so you have another 2 electron because carbon has 2p2. So now you have 8 electrons altogether. So then you can put another more 2 electrons here. So it will generate this situation, whereas you have 1 sigma 2, 2 sigma 2 and 1 pi 4. Okay, so this configuration shows that carbon 2 molecule will be diamagnetic. So this is paramagnetic and carbon 2 is diamagnetic because there is no unpaired electron. Now let us consider the case for nitrogen. For the nitrogen you have another 2 electrons and you will have total of 10 electrons here because it is 2p. So basically it is 2p3. So now you will have 10 electrons and you can place these 2 electrons in the 3 sigma orbitals, and it will also be diamagnetic. N2 will also be diamagnetic, and you can now you can calculate the bond order for these molecules. Let's say for example N2. For N2 molecule you can see this 1 sigma is filled, this 2 sigma is filled, and this 1 pi is also filled. Okay, now bond order means you have to count the number of electrons in the bonding orbitals and subtract and you have to subtract the number of electrons in the anti-bonding orbital, and then you have to divide that number by 2. So now we have to count the number of bonding electrons and number of anti-bonding electrons, or in this case actually not number of bonding electrons, but it is actually the number of bonding and non-bonding electrons. Okay, so in this case you can see this 1 sigma orbital is a bonding orbital, this 2 sigma star, it is actually a 2 sigma star orbital, or it is an anti-bonding orbital, whereas this 1 pi it is a bonding orbital, and this 3 sigma it is a non-bonding orbital. So total number of bonding and non-bonding electrons in this case is 2 plus 2 plus 2 plus 2. So that means 8 number of bonding and non-bonding electrons, whereas 2 electrons are also there in the anti-bonding orbital. So we have to subtract 2 and divide it by 2. So we will have 6 by 2, that means 3. So in this case the bond order is 3, and which is equivalent of saying that nitrogen has 3 bonds. Okay, so we say that nitrogen has 1 sigma bond and 2 pi bond, and the same is represented by here. Okay, now next we can count for carbon also. So let's say here you have carbon. So for carbon these 2 orbitals will be not there, this non-bonding electrons will be not there, and in this case you can see the number of bonding electrons are 2 plus 2 plus 2 means 6, and number of anti-bonding is minus 2. So that means it will be 4 by 2, and it will be actually 2. So bond order for C2 molecule is 2. So carbon-carbon double bond is there in the imaginary diatomic carbon molecule. But most important thing here is that you can see in that molecule there is no sigma bond, there is only pi bond, because sigma bond is cancelled out by 1 sigma and 1 sigma star. But the carbon 2 carbon atoms are held by only a pi bond. This is a crazy outcome, that the orbital energy shows that the carbon atom in CC bond there is only pi bond and no sigma bond. So this is a MCQ question from competitive exam, that they can ask you that in carbon atom what type of bond is there, whether it is sigma bond or it is pi bond. So you have to say that 2 pi bonds are there, no sigma bond is there. And in case of boron, you can see it will have lower two less electrons, and that means here you will have 4 minus 2 by 2, that means 2 by 2, and it is actually 1. So for boron, the bond order, so for B2 molecule, the bond order is 1. You can see the bond order is 1. So this is the case of diatomic molecules for boron, carbon and nitrogen. Now let us move towards the oxygen and fluorine. So basically the molecular orbital diagram will be similar but slightly different, because in this case these are in the periodic table, they are more at the more right hand side than these molecules, and that's why the energy separation between the 2s orbital and the 2p orbital is higher for these two molecules, or onward the nitrogen molecule. So in this case we will represent it by like let's say here you will have 2s orbital and here you will have the 3 2p orbitals, and you can see the energy separation is higher. So if for these diatomic molecules the situation is like this, then for these molecules it is higher, so this energy separation will be higher, and due to this higher energy separation between 2s and 2p orbitals, no mixing will occur. So in the previously we mixed up all the four 2s orbital and 2p-z orbitals, that 4 orbital mixed to give 4 molecular orbitals, but this situation will not occur for these two molecules because their energy separation is higher. So in this case we will represent the molecular orbital diagram like this. So this is one, so this is basically 1 sigma, this is 2 sigma, or you can say 2 sigma star, whereas now 2 other sigma bond will be formed by the overlap of the 2 2p-z orbitals. So this is basically 3 sigma and this is 3 sigma star, and pi bond will be the similar. So this is 1 pi and this is 2 pi star. Okay, now the basic difference between this molecular orbital diagram and the previous one is that you can see in the previous one you had like this. So this is your 2 sigma and this is your 1 sigma, and this is your 1 pi, and this is your 3 sigma, this is your 2 pi, and this was your so basically this will be 4 sigma star. Okay, so this is 4 sigma star. So basic difference is that you can see this pi orbital had lower energy than the sigma orbital, whereas in this case the 3 sigma orbital has the lower energy than the pi orbital. So this is the main difference you have to note between the boron. So this is for boron, carbon and nitrogen, and this diagram is for oxygen and fluorine. So this is the main difference. So whenever you are filling the orbitals with electrons, the order of filling will be different. So in this case, let's say we consider oxygen. So oxygen has 2s2 2p4. Okay, so if we consider total of 12 electrons, so 12 electrons will feel like this 2 2 2 2 and 2. So this is 1 2 3 4 5, and another 2 electrons will be here. So you can see the 2 electrons will be placed in the pi star orbital, and this is why the oxygen molecule will also be paramagnetic. Oxygen molecule will be paramagnetic because you can see 2 unpaired electrons are there. And if we consider the bond order of this molecule, we can say that so basically you can see in this case this bonding situation is cancelled out by this anti-bonding situation. So whenever we are considering the bond order, we don't have to calculate this, we have to calculate only this situation. And here you have 6 bonding electrons and 2 anti-bonding electrons. So that means 4 by 2, that means 2. So bond order for oxygen is 2, and we know that we represent oxygen by this. So it is implies that 2 oxygen molecules are held by 1 sigma bond and 1 pi bond. So this is basically the completely different situation from a C2 molecule. For C2 molecule, we knew that the occupation of the orbital was like this. So C2 molecule has total of 8 electrons. So the 8 electrons filled like this. So you can see, although in this case 8 while we are filling the 8 electrons, we first fill the 1 pi orbital, but in this case we can say we first fill the 3 sigma orbital and then the 1 pi orbital, and this makes the difference that C2 molecule was, so this C2 molecule, this was diamagnetic. If the molecular orbital diagram for C2 molecule would be same for that of oxygen molecule, then you can see that if the energy then the energy difference would be reversed, and you should first fill the 3 sigma orbital and then you will have the 1 pi orbital with the unpaired state, but that doesn't happen because in this case the sigma orbital has the pi orbital has lower energy than the sigma orbital, and this situation doesn't occur. So this is the basic difference between the oxygen and fluorine and the other molecule. And if you consider now the F2 molecule, you will have to put another 2 electrons, and this will make the bond order 1, because now you can see this will be 6 minus 4 situation, and it will be 4 actually 2 by 2, and this 1, and also it is now diamagnetic because there is no unpaired electron. So this is the basic bonding situation for your diatomic molecules, homonuclear diatomic molecules. Now let us talk about hetero. So from this discussion, the point you have to notice is that the energy order is different for these two cases. For oxygen and fluorine, the 3 sigma has lower energy than 1 pi, whereas for carbon, boron and nitrogen, the 3 sigma has higher energy than 1 pi. 2 sigma is always lower, but the difference is between 3 sigma and 1 pi. So several questions is asked from this particular concept. Now let us talk about the situation for CO and NO. Okay. So for CO and NO, basically they will behave same like the homonuclear diatomic case with the lower atomic number, like for example boron, nitrogen and carbon, because carbon is there which has lower electronegativity, and in these cases for CO and NO the mixing of 2s and 2p orbital can occur. But in this case the main difference is that you can see if we represent these 2p and this is the let's say this is the 2s for carbon, then for oxygen we have to represent like this. So here the oxygen will have 2p here and the 2s will be here. Okay, so this is 2p, this is 2s, and this is for oxygen. Now you can see that this energy difference is higher than this, and also overall the energy of the 2p and 2s orbital will be lower than that of carbon because oxygen has higher electronegativity. Now these 4 orbitals, these 2 2s and 2 2p's, they will combine to form 4 molecular orbitals like this. Okay, so another 2 will be here basically. Okay, and now you can see the pi orbitals will also be there, so these will be basically the pi orbitals. So actually we should represent it like this. So basically here it will have, and you can see here it will have the pi electrons. So basically I should write it just little above for the sake of simplicity. This all are arbitrary and you can adjust it according to your ease. And now here you will have the pi bond. So this is your pi bond and this is your sigma bond. Okay, so you can see this is 1 sigma, this is 2 sigma, this is your 3 sigma, this is your 4 sigma, this is your 1 pi, this is your 2 pi. Okay, now the carbon atom will have 4 electrons and the oxygen atom will have 6 electrons. So overall 10 electrons are there, and we have to fill accordingly. So 2, then 2, then another 4. So 8, and this is 2. So these are the filled orbitals for your CO molecule. Now in this case we have to look at the structure of the orbitals or the shape of the orbitals, and the point of interest is this 3 sigma and this 2 pi. So in the previous case whenever bond was formed between two molecules of same nucleus in the shape of the pi orbital, or let's say we take only the shape of a sigma orbital formed by overlap of two p orbitals, so the shape would be like this. Okay, so it will have a symmetrical shape of the sigma orbital, but in this case you can see the carbon has lower electronegativity than oxygen, and that's why the bonding orbital will have more coefficient on the oxygen and less coefficient on the carbon, whereas the anti-bonding orbital, let's say pi star orbital. So if we represent the pi star orbital of a CO, so this is basically the representation of carbon monoxide. So pi star orbital will have higher coefficient on carbon and lower coefficient on oxygen, whereas the pi orbital will have higher coefficient. So basically this will look like this. Okay, so you can see higher coefficient is on oxygen and lower coefficient is on carbon for the pi orbital, whereas for the pi star orbital the situation is reversed. Why? This is because you can see this is basically the pi star and this is basically the pi. So you can see the energy of the pi orbital is closer to that of the oxygen. So that means its structure will also resemble that of the oxygen, or its coefficient will be more on the oxygen atom, whereas the energy of the pi star orbital is closer to the energy of the carbon, and its structure or shape will be also be similar to that of carbon 2 p orbital, and that's why the coefficient will be higher on the carbon. So this is why their shape will be reversed, and it has a far-reaching implement on the chemistry of the molecules while we will discuss about the organic reaction mechanisms. So now let us talk about NO molecule. Okay, so NO molecule, or we will represent the NO. So CO and NO will have same structure. Here we have to just alter it. Here will be N, it will be O. Now the NO molecule, for NO molecule it will have for nitrogen it will have 5 electrons, and for oxygen it will have 6. Total 11 electrons are there. So basically one extra electron will be placed in the pi star orbital, 2 pi star orbital. And now in this case, if we consider the bond order, you can see so this bond, you can see this sigma bond is cancelled out by this sigma star, so we don't have to count them, but we have to count only this portion. And here you will have 4, 2 plus 2, 4, so 4 bonding orbitals, and this one is non-bonding. So this 3 sigma is actually a non-bonding orbital. So 4 plus 2 minus 1, because this is anti-bonding, by 2. So that means 6 minus 1 by 2, so 5 by 2, that means 2.5. So for NO molecule you can see it has bond order of 2.5, whereas for CO molecule, you can see for CO molecule, if we count that 2 pi star was not there, so it has bond order of 4 plus 2 by 2, that means 6 by 2 equal to 3. But you can see for from the NO molecule, so this is why NO molecule is represented as a pi star free radical. It is frequently said that NO is a pi star free radical because one extra electron is at the pi star orbital. So that's why it is called a pi star free radical. But you can see if we can remove this one electron and if we generate NO plus, then we can see that this electron is removed and now the bond order will be 3. So if we remove one electron from the NO molecule, we will transform the bond order of NO molecule from 2.5 to 3. That means NO molecule will be stabilized. Whereas if we put one more electron and form NO minus, then this extra electron will be put into this pi star orbital, and you can see now the bond order will be reduced and it will be now 2. So if we add one electron in the NO, it will have bond order of 3, and if we add one electron, the bond order will be 2, and if we remove one electron, the bond order will be 3. So this is this question also comes in the exam. So this is the molecular orbitals of the diatomic molecules, and with the homonuclear diatomic and heteronuclear diatomic. So in the next video I'll be directly move on to the organic reactions, that is how the reaction happens and what are the frontier orbitals or frontier molecular orbitals, the concept of HOMO and LUMO, and the concept of nucleophile and electrophile in terms of molecular orbital point of view. So if you like this video, then give a thumbs up, and if you are new to this channel, then subscribe my channel, and thank you for watching.